So in this case, well, as opposed to the square root, for the cube root we can find cube roots of negative numbers, like the cube root of negative 8. So in this case, for example, can you find what number squared equals negative 4? There's no way, because every time we square a number, that is, every time we raise a number to an even power, there's no way we can get a negative number. But it is possible for cubes, because when we move, and the answer here is negative 2, because negative 2 times negative 2, that's positive 4, times negative 2, that's a negative 8. It's possible for odd powers, and therefore that's why we will have a function whose domain, it's all real numbers. So the pattern is the same: even index, restricted domain to 0 to infinity; odd index, no restriction, the domain is all real numbers. The next category of function, and this is the one that you might want to take into consideration when it comes to finding infinite limits in the next section. It's important to look at the shapes of these functions, of the reciprocal function. Well, in this case, we have the simplest case that you have used before, right? The graph of 1 over x, having the two tails of the graph pointing in different directions. But when it comes to having the function y equals 1 over x squared, the difference is that in this case the two tails point towards the same value. And again, these ones are very, very important when calculating limits. For example, later we will do calculations about limit f of x, or limit of 1 over x as x approaches 0. But in this case, we need to approach from the left. Where is this number going to when we approach 0 from the left? To negative infinity. And then we're going to do this approaching from the right. Where is this going to go to? Positive infinity. Well, what if we want just plain vanilla 0? I mean, in this case, so we can evaluate this limit exactly at 0. We need to make sure that the limit is going towards the same point on both sides. But in this case, because this is going in two totally different directions, we will later see that this is DNE. The limit does not exist. This won't be the case for the even power in the exponent, because limit 1 over x squared, x approaches 0 from the left. X approaches 0 from the right. Oops. 0 from the right, and limit x approaches 0, plain vanilla 0, not left, not right. Okay, let's analyze the graph. Approaching from the left, where is the value of y going to? Positive infinity. Approaching from the right, also positive infinity. Well, in this case, the limit on both sides agree, right? That means that exactly as 0 is, this is not going to be a DNE, that's actually going to go to positive infinity. Yeah, well, it's technically an inexisting limit because it's infinity. But the difference here is, for the previous case, we have a limit going to the negative direction and the other one going in the positive direction. And of course, it's important to understand the shifting. That's what we're going to do next time. For example, f of x equals 1 over x plus 3, quantity squared. Alright, so this plus 3 means that we need to shift the graph 3 units in which direction? The left or the right? To the left. Alright, so that's going to translate a vertical asymptote like this. Alright, but that's not the correct one, right? Actually, they're both pointing up in this case. Okay? But well, shiftings and translations, we're going to do that next time. However, I wanted to stop a little bit and discuss a little bit more on these reciprocal functions, because we will use this a lot in the limit chapter. All right, so what do we have right here for the next page? Exponential and logarithmic functions. You know, exponential functions, you can always relate to what they relate them to the purpose, to the main purpose of this kind of functions, which is mostly modeling exponential growth, right? The population growth or radioactive decay. Well, how do we know which one is which? Well, the one that grows to positive infinity, that's the case in which we have a positive exponent. But otherwise, we have a decaying function when the exponent is negative. Okay? So these kind of functions, you will later use them when modeling electrical circuit situations, in chemistry when dealing with chemical kinetics, and well, you'll see a lot about that when you get to those courses in electrical circuits, physical chemistry, what else? Also in classical mechanics, a lot of the models about in forces are also modeled by exponentials. And of course we have the logarithmic function, which is really the inverse function to the exponential function. All right. And the last group of functions is the trigonometric functions. Well, last time we reviewed how to find the values by number one, either using the unit circle or the special triangles. And again, when it comes to quizzes, exams, you're more than free to use either one or the other, unit circle, right, or the special triangle, whichever you feel more comfortable with. Okay, and well, as far as the graphs of the trigonometric functions go, of course there's 6 functions, but typically we use the most important of the 3, which is sine, cosine, and tangent. Well, the main difference is, well, sine and cosine, their shapes, they're both exactly the same. Also, it's important to denote a very, very important property of these functions, which in this case is their period. And the period is the value at which this function completes one cycle. And does anybody remember what's the period for the sine function? 2 pi. All right. What about the period for cosine? Also 2 pi. What about the period for tangent? Careful. This one is pi periodic, right? That means that this. So here you can see it from the picture for the tangent function. In this case, it completes a cycle between between negative pi over 2 and pi over 2. That's 1 unit of pi. This is going to be very important in the second exercise when we find domains of involving trigonometric functions. All right. So what do we have? What else we have? Okay, another difference between the sine and the cosine function. One of them is even. One of them is odd. Which one is which? Which one is the even one and which one is the odd one? Looking at the pictures. Yes?
Are perhaps sine and cosine even where tangent is odd, or?
Well, tangent is odd. And that's true. What about sine? This one is also odd, right? And how do we know it's odd? Well, from the graph, notice it's symmetric about the origin, whereas for cosine is symmetric about the y-axis, and that's even. And well, one way to determine the parity of the function tangent is, well, looking at the graph. It's also symmetric about the y-axis. However, if you define y equals tangent as the quotient of sine over cosine, all right, that's one of the identities. Well, sine is odd, cosine is even. What do we get when we divide an even quantity over an odd quantity over an even quantity? It's going to be an odd one, right? So, okay. Let's look at this first exercise right here, and let's see. Match the equation with its graph. So we have 4 graphs. They are all defined in terms of y equals 3x, x cubed, y equals 3 to the x, and y equals the cube root of x. And the graphs are labeled with letters. So let's see if we can match them. Okay. Y equals 3x. Which one from this graph would be? The green one, which is labeled with a G, right? What about letter B, 3 to the x? It's an exponential function. What else? The sign of the exponent. Well, I don't see any negative sign, so when it's positive, it should be an increasing exponential, right? Which one would be? F, the blue one. Which F? The lowercase f, right? What about C equals y equals x cubed?
Yes, sir.
It's a big F?
Yes.
That's the red one. And well, the last possibility is little g. Okay? So, very simple exercises, just going with the shapes. But in the next section, we're going to look at the shifted versions of these functions. But one of the core topics when it comes to that we need to bring into calculus is how to find the domain of a function. So all these guidelines that I have summarized for you here, you learned it throughout your years in algebra whenever you were learning a new kind of function. Well, when it came to linear functions, you calculated slopes and found equations of parallel, perpendicular lines, and whatnot. And well, then the domain of those functions were always all real numbers. And then you move on to quadratics, polynomials. They also had non-restricted domains, and that's what we have on the first part of the guidelines. Whenever we have polynomials and the trigonometric functions sine and cosine and radical functions of odd index, as we already discussed from the different shapes that we covered in the previous page, all you have to write down is all real numbers, no more, no less. You don't have to do any work. But now, when we have radicals of even index in this case, what we do in this case is set the radicand greater than or equal to 0. That's how we exclude those negative numbers, right? And then solve the inequality for the given variables. Okay? And whenever we have a logarithmic function, it's going to be similar to radical functions. In this case, we are going to set up the argument. The argument is the expression inside of the logarithmic function. And in this case, we set it only greater than, not greater than or equal like the radical. And the reason why we set it only greater than and not equal to 0 is because can we evaluate the logarithm of 0? What is that? Isn't that just undefined? Okay, well, evaluating the function is undefined, but when it comes to finding the limit, which we will see later, that's going to go to negative infinity. Two very apparently similar concepts, but really very, very different. Okay. The other piece of information for finding the domain of a function, well, when it comes to having a rational function, and a rational function is defined as a quotient of two polynomials. So not because you see a quotient, it's a rational function. Well, the pure definition is just polynomial over polynomial. Of course, when it comes to other combinations of functions, we will use the same guideline to find the domain. And well, so what we do when having such kind of functions, we want to make sure we need to be aware of those values that make the denominator 0. So in that case, what we set is set the denominator not equal to 0 and solve for the given variable. Okay, that's how we exclude the domain. I mean, it's like a lot of words in here, but how about we see this in action? Let's see what about the next page. Find the domain of each function below. F of x, for letter A, f of x equals x to the 7 minus 3x to the 5th minus 12x. What kind of function is that? Okay, what's the domain of a polynomial? All real numbers, all that. That's it. And be sure to have parentheses around the infinity symbol. Recall that we cannot use the brackets around the infinity symbol because we would think that it's exactly infinity, like infinity would be a number, but again, infinity it's not a number. Infinity is just an idea of something that never ends. Alright, so that's why we leave that interval as open, because it keeps getting bigger and bigger and bigger every time. For letter B, f of x equals 1 minus 3x, x times x minus 11, 7x minus 41 divided by x to the 5th minus 14x to the 4th plus 48x cubed. Alright, number 1. Yes, this function looks funky with the numbers and powers and everything, but ultimately, as a bigger picture, what kind of function is it? It's a rational function. So what about rational functions? Can we plug in any number? Just any number? What are the restrictions of a rational function? Yes?
0.
Well, 0 is one of them, but in this case, we need to find all the possible values that make the denominator 0. And in this case, what we're going to do is set this quantity and set it not equal to 0, because we don't want those values, right? Well, so in this case we need to solve this equation, this polynomial equation. Any ideas on how to go about it? Factor out. So factor the GCF first, and the GCF seems to be x to the cube, x to the third power, and we will be left with x squared minus 14x plus 48. Alright? Any ideas on how to factor the polynomial inside of the parentheses? So in this case, for the polynomial inside parentheses, we can use the double bubble method because the leading coefficient is 1. And in this case, we can just put the x's and find factors of 48 that add up to negative 14. 6 and 8 are the factors because 6 times 8 equals 48. But wait a minute, we need the addition of the numbers to be negative. So both have to be negative here. Alright? And still, it's true that negative 6 times negative 48, it's still positive 48. Alright? We don't want these values to be 0. That means x cannot be 0, x cannot be 6, and x cannot be 8. Alright? Those are the numbers that when you plug into that function, the denominator is 0, the function is undefined. And of course, there's several ways to represent this result, and we're going to use all of them. The graphic representation and interval notation for it. It's very important to know how to represent this in that notation. So I'm going to plot a number line, a real number line, but I'm going to focus on these numbers that get actually restricted from the domain of the function, and those values will be represented with open bubbles: 0, 6, and 8 in this order from smaller to large. So that means this function is the okay input for this function is this interval, accept that value, this interval, accept that value, this interval, accept that value, and this interval all the way to infinity. So let's describe these intervals using interval notation. Well, what does the arrow imply here? It's coming from negative infinity, negative infinity, and then we stop at 0, 6, and 8. Negative infinity to 0, close, open, actually parentheses because we need to exclude that, union, 0 to 6, close parentheses, to exclude the value of 6, and another union symbol for 8 to 6 to 8, right? 6 to 8, and union 8 to infinity. All right, so that's the domain of this function, represented using graph, represented using interval notation, the same notation that we reviewed last time, I think, or last week. Remember all these different cases we did question?
Yeah. So this is like the domain as minus infinity to infinity, and then C at excluding 6, 0 and 6.
That's another notation. I mean, another way to denote x such that x is all real numbers except x equals 0, 6, and 8. That's another way to write it, but typically we would be looking for interval notation, all right? And the graph whenever possible. The more information and the more explicit that we are about it, the better. Okay? So, let's look at letter C, the square root of x minus 3. Well, so this is a radical function, and we happen to have an even index. Will this function have a domain of all real numbers? No, right? Because that's an even index. So in this case, what do we do for radical functions of even index? Set the radicand greater than or equal to 0 and solve the inequality. X minus 3 greater than or equal to 0, and well, this one requires one single step. X greater than or equal to 3. Alright? So, or using graph notation, 3 and actually solid bubble, right? And oops. And this is the domain, all right, from 3 all the way to positive infinity. Natural log of 6x minus 5. What do we do for logarithmic functions? Let's go back to the instructions, the guidelines to find the domain. Very similar to the radical one, right? Except that we don't include, we get rid of the inclusion here. So this would be 6x minus 5 greater than or equal to 0, just greater than, and 6x greater than 5, and x greater than 5 over 6. Alright? Actually, we should represent the previous one using interval notation. That's from 3 to infinity, brackets for the 3 because it's inclusive on the lower endpoint, and infinity for, and parentheses for infinity. In this case, for the logarithmic function, this will be parentheses for 5/6 and parentheses for infinity. Alright, when it comes to, so here we're going to have a combination of fractions and trigonometric functions. Of course, I mean individually, the domain of sine 2x is all real numbers. The sine function doesn't have any gaps, doesn't have any asymptotes like the tangent function, and same for the cosine function that we have in the denominator. However, as an overall function, there's issues with the domain, so we want to make sure that 1 minus 2 cosine x is not 0, because what happens if that quantity is 0? It becomes undefined. So let's set the denominator equal to 0, that is 1 minus 2 cosine x equals to 0, and solve the trigonometric equation here, in this case negative 2 cosine x, and that equals to negative 1, and cosine x equals to negative 1 over negative 2, which is 1/2. Okay guys, so yes, this looks like very simple algebra, I mean solving for the cosine function, but this is going to go a little bit beyond than solving an equation for a variable x. It's not just going to go like the ones we did before, like 6x minus 5 greater than 0, and then when we set up the polynomial not equal to 0. And the issue here, and rather what we have to take into consideration, is the fact that trigonometric functions are periodic, and not only that, a cosine function for some value may have more than one possible answer. Well, in particular, two separate answers. Number one, let's remember that all students take calculus mnemonic to determine the quadrants where the trigonometric functions are positive. Well, in this case, we want cosine to be positive 1/2. Which quadrants is that? The first and the fourth one, right? So that's 1/2. Oh, wait a minute. 1/2 and 1/2. All right? Because that's adjacent over hypotenuse. So the opposite in this case will be root of 3. And of course, you can. I'm going to do it using the representative triangles. In this case, this is 60 degrees or pi over 3, and this is 300 or 5 pi over 3. Another way to get these results is using the unit circle, and let me show you the unit circle way. The unit circle, which is right here. So we're looking for the values of the angles for which we have a cosine equals 1/2, isn't it? Cosine, the x coordinate, pi over 3, and also pi over 3, 5 pi over 3, giving us the cosine being positive 1/2. Either way you do it, the unit circle or the triangle, you should get the same thing. Now, here is the thing. Here is the thing. So in this case, these are not the only solutions. We need to keep in mind the periodic property of these trigonometric functions. That means, in this case, then, x cannot be pi over 3 plus 2k pi. What is this 2k pi? Remember what we analyzed as well about the periods of the sine, cosine, and tangent functions? Because what happens when you add 2 pi to pi over 3? Don't you get really to the same point on the circle? And that's the same value. So in this case, we're getting infinitely many points for which x cannot be 0, and also x cannot be 5 pi over 3, also plus 2k pi. Multiples of k pi, and this could be whether in the clockwise direction or in the counterclockwise direction. All right, let's do a similar example, but now one with tangent. And again, this one looks similar, except that our denominator is 1 plus tangent. So in this case, the result and the way we're going to tackle the problem it's going to be very, very similar. However, okay, let's see, let's set up 1 plus tangent x equals 0, 1 tangent x equals to -1. Well, so number one, this is the same as saying -1/1. This, so we can see it as a ratio of numbers, so we can find the corresponding triangles or angles. All right, again, all students take calculus. All right, and we want this time we want tangent to have what sign? Positive or negative? Negative. What quadrants have tangent negative? Second and fourth. Do we all agree with second and fourth? Yes? Okay. So second and fourth. Okay, so this is -1/1, opposite over adjacent, opposite over adjacent. All right? Well, number one, what special triangle is this? Which angle is, what's the acute angle right here? It's a 45-degree, but in this case, because of the position on the Cartesian plane, it's on the second quadrant. That's 45, 90, 135, that's 3 pi over 4. So, on the one hand, x cannot be 3 pi over 4, alright? And, well, for now. And also x cannot be, well, that's also a 45-degree angle for this triangle, but I mean, given the position, given the actual position, we go from 0 all the way to 7 pi over 4, okay? So it cannot be 7 pi over 4. But in a similar way, the functions related to tan are also periodic, so if we add 2 pi, oh well, for each we add 2 pi, alright? 2k pi, 2k pi. That's individually. That's if we split this into two separate answers. However, so that's one version. The other version is just considering x equals 3 pi over 4, and in this case plus k pi. Either one or the other is fine because, well, if we are at 3 pi over 4, we add a multiple of pi, that is, we are 180 degrees. Isn't it the second solution? And then, so either way, you can express it as two separate expressions or single expression. All right. So when you see this, something like this on a quiz or an exam, either of the two boxes is acceptable. Okay. Whether treating it as a single, as a compressed single answer or as a separate answer. Question.
So also for question B, we can kind of simplify it just how we did for question F.
Which one? Here?
Yeah. Like the
simplify the
can we like also, I guess, like trim it down to one equation?
Oh, not in this case, because so for example, the distance between pi over 3 and 5 pi over 3 is not 180 degrees, and also this distance right here is not 180 degrees either. It's something else. The tangent function is a very particular one that has the 180 degrees between each asymptote, and well, sine and cosine doesn't have those asymptotes. All right, guys, one more. Finding the domain of this composite function. Whoa, so f of x equals e to the 1 over x plus x cubed over x squared minus 16 plus log of x plus 2. Well, what are we going to do to find the domain of a function like this? And well, let's look at each individual term. So this is what we're going to do. Let's call this A, B, and C for every single term. And we're going to look at their restriction for every single term. Okay. Number one, e to the x. So the exponential function doesn't really have a restricted domain. You can plug in every single value and you'll have an output for it. However, this particular exponential function has as an exponent 1 over x. Do you see the restriction there?
0.
So we cannot plug in 0 for this function, right? So for the function a, all these values except 0. Oops. Okay. Okay, let's look at part B. Actually, let me use different colors for every different function. Okay, so part B. For part B, individually, it's a rational function, and we don't want the denominator to be 0. So for B, let me do the calculation for B. We don't want x squared minus 16 to be 0. That's a difference of squares. And well, x cannot be negative 4, and x cannot be positive 4. Those are the restricted values for the second term. Are you guys following me here? Okay, let's plot those. So negative 4 and positive 4. All right, we're almost done. Just give me maybe an extra minute. So okay, let's shade the OK inputs here. All right, and let's do letter C. What about log of x plus 2? Well, on the one hand, we don't want x plus 2. We just want it greater than 0. That's x greater than 2 only. All right. So what about this? So when we put, then yeah, that's what I meant. Yeah, negative 2. Negative 2. Okay, so C. In this case, negative 2, which is right here, somewhere here, and shade. All right. How are we going to find the overall domain? To find the overall domain of a composite function such as this, find the intersection between the three sets. In other words, think of doing like a sandwich with those shadings here. The result will be, okay, A intersection with B, intersection with C. In other words, the overlaps of these three sets. So in this case, what are the sets that are in common? Actually, no, not this one, right? Not this one. Okay. The most restricted function right here is the one in purple, right? Which is the logarithmic function. So this is not going to be part of the domain. This is not going to be part of the domain either. So truly where there's overlaps here is here. Whoops. Is here and here and here, all right? Those are the three intervals where we have overlaps. Let's write this down using interval notation. So that's from negative 2, 0, and 4. So from negative 2 to 0, the union from 0 to 4, and from 4 to infinity. I don't think you're not for sure gonna get anything like this on a quiz or an exam, but the reason why I'm coming up with something this big is so we can put everything together and recall how to find this by overlapping sets, right?